Hey there everyone, Lee here, and welcome to part 4 of 6 of my Santa platformer game tutorial. In the last video, we created an animation controller as well as several little animations for our Santa player. We also modified some code so we can change the state of the animation and have it change based on the actions of Santa. In this video, we will take our dash and butt slam abilities and add after images for when these abilities are activated. We will do this by use of object pooling. If you haven't already, be sure to check out the previous videos. We're more than halfway through this series, so let's just get right into it.
To start, we'll need to go to our scripts folder and create a new C# script. We'll call this after image. In our script, we'll need a few variables. First, we will need a float called image rate. When an after image is created, there will be a duration of time in which the next image is made. Image rate will represent this in seconds. Next, we will need image life, which is simply the total time it would take for an image to generate, then disappear completely, also in seconds. We'll also need a start color. We want to be able to change the color of the after image depending on the ability used. We also need to use this to determine how to fade to nothing, which I'll get more into later. As I mentioned earlier, we'll be using object pooling. I won't get into details just yet, but just know that we will need a queue of type GameObject called ImageQ, and we'll need to initialize this now with a new queue GameObject. We'll also need a GameObject that represents the next in queue. We will need a function that automatically spawns a new image and fade it out every time it's called. We'll call this function spawnImage. For the logic, we first want to create an empty game object that will contain the current sprite. To that object, we'll attach a sprite renderer, and then have that sprite renderer copy the current sprite that this game object is currently using. Then we copy the current position and scale, and make sure the image is exactly where the player currently is, and is facing the right direction. And finally, we'll use a coroutine to fade out the object. We won't need the entire game object, so we will only pass through the sprite renderer. To create the game object, we'll set it to a variable obj and instantiate it. Since we'll need a sprite renderer later, we'll create it as a variable as well, sr, and add it to obj with add component sprite renderer. This line should have been under the next comment, but it's a thought that counts. We will then assign sr.sprite to the current sprite with getComponent sprite renderer.sprite. For the position, we'll set obj.transform.position to this object's transform.position, and we'll do the same with a local scale. To fade the sprite, we'll use a coroutine, i.e. numerator fade image, that takes a sprite renderer. We'll need to create a target color based on the start color and set the alpha to 0. This way we have a start color and an end color in which we can transition to. We'll also create a time counter, since we'll need to keep track of the time and ensure it fades after the duration we set with image life. To change the color, we'll use a while loop and a lerp. We will add time to the time variable with every pass of the loop. Once time exceeds the image lifetime, we will stop the loop. And while the loop happens, we'll change the color based on the current time with respect to image life. After the while loop, we will manually set the color to the target, just in case somehow the while loop doesn't set the color to the final color exactly. First, we create color target equals start color, then change the alpha with target.a equals 0. We'll create the time counter, which is float time, and we set that to 0. We'll now create a do while loop, and the condition is that time is less than image life. First, let's make sure the loop will end eventually with time plus equals delta time. This just adds computational time to time, and will accurately count down real-time seconds. Then, to change the color, sr.color equals color.lerp, start color, target, time divided by image time, just to ensure that the last argument is a value between 0 and 1.
For the lerp, there will be 3 arguments. The first argument is where we want the thing to start at. The second argument is where we want the thing to end at. And the last argument will be a value between 0 and 1. In the case of color.lerp, the first argument will be the starting color. The second argument would be the color that we want to end at. In this case, we want the alpha to be 0. And for the last argument, a value between 0 and 1, you can think of it as percentages. You can think of lerping as a slider, which I will use a pencil here. The starting color will be at one point. The ending color will be at the other point. And the value of 0 to 1 will be any point along the slider. As we increase the values, we are simply going up the slider into the other color.
Because this is a function for a coroutine, at some point we will need to write a yield. Since we don't need to wait, we can write yield return null. Lastly, we can set sr.color equals target. Now that we have the coroutine, we can start coroutine, fade image, and pass the sprite renderer sr. We'll need functions to get the images to start, stop, and even change colors. Our start will be public void start after image. We'll also need a public void stop after image. And lastly, we will need a set color that takes color C. And this we can just fill in, since it will be just start color equals C. For the start, we want to make sure we are only leaving one trail, so we must stop any previous calls to create images. To start the image, we will need to invoke a repeating function at the rate set by image rate. For stopping, we've already created a function even if it is empty, so we can just call that. For invoke repeating, the first argument is the name of the function we want to repeat, spawn image, which will be in quotes. The second argument is the delay that it would take for the first call, which we want to be instantaneous, so it'll be 0. The last argument will be the rate in which the function is repeated, which we have defined as image rate. In our stop function, we'll cancel everything called with invoke repeating by using cancel invoke. To get this to show, we'll need to call these functions. So for now, let's set it in our start function. We'll first use set color and let's set it to red. Then we'll call start after image. Back in our scene, we can drag that new script into our Santa game object. We'll set our image rate to 0.05 seconds, which will be super fast. The life of the image will be 1 second. When we hit play, we can see our after images. But you will notice the images are drawing over Santa, causing this glitchy effect. We can easily fix this by changing order and layer in our sprite renderer. We can just bump this from a 0 to a 1. and now it works as it should. But you might notice in our hierarchy that new game objects are being constantly added. This might be taxing on the performance later on, so this is not a good idea. We'll be fixing this issue with object pooling.
So when we're talking about object pooling, we are simply talking about reusing objects that are already existing in our level. You'll find that a lot of games actually use object pooling. When we defeat an enemy, there's no need to actually destroy the enemy. We can just hide it away. When we're ready to reuse it, we can just plop it onto the level. In the case of our after image, we'll start with an image that is fully solid and visible, and then we're going to slowly fade it out to nothing. When the alpha is 0, it's essentially hidden and the players won't actually know it exists. When we're ready, we can take that faded game object and make it fully visible again and fade it just like we did in the beginning. It takes a bit of work to reinstantiate a game object, so since we already did it, why do it again? We can just reuse everything. And with object pooling, we can simply use an array, but there's other types of data structures that function in a similar way to an array that will better suit our needs. In this case, we're going to use a queue. A queue is no different than a line at, say, a store. The idea is the first one in, the first one served. And when that first person is finished being served, he'll simply move out of line and the next person can be served. We'll do something similar with our after images. The first image in our queue will take time to fade out. Once it's faded out completely, we'll just move it to the back of the line. And then we'll keep on repeating this process for as long as it's needed. And the only time we'll need to create a new game object is if the game object in the front of the queue hasn't finished fading out. If it hasn't finished, we'll add more game objects to the queue, and if it is finished, we can just move that one to the back of the line and we won't need to recreate anything new.
Earlier, we've already created our variables necessary for our pooling. We have a queue, and we have a game object for when we remove the next object in the queue, called dequeuing in C#. Every time we dequeue, we will need to assign it to this next in queue variable. In our spawn image function, we'll start off by the dequeuing, but we need to give proper conditions for when to dequeue and assign it to next in queue. First, if next in queue is null and our queue is not empty, or if next in queue is not null and the alpha of next in queue is less than or equal to 0, which means it has completely faded. Then we can dequeue and assign it to next in queue. For the next part, as I was editing, I realized that I could have put it in the previous statement, but as before, if next in queue is not null and the object has faded, assign obj to next in line and grab the sprite renderer into SR and set next in queue to null. Otherwise, we'll create an empty game object and sprite renderer just as we did before. The last thing we will do is add obj to the queue. Let's code. If next in queue equals null and image queue.count greater than 0, or if next in queue not equal to null and next in queue.getComponent sprite renderer color.a less than or equal to 0. We'll assign next in queue and dequeue using next in queue equals image queue.dequeue. The next if statement we'll copy from above. And then we'll move the creation of the obj and SR variables to just before the if statement. Since the else will largely be the same as our previous code, let's set the assignments here. I'll delete these declaration statements, since the objects have already been created. And we'll also delete these parts here. Inside the main if statement, we'll set obj to next in queue, sr to next in queue.getComponent sprite renderer, and then set next in queue to null, so the previous if statement knows to reassign it later. Finally, at the end, we'll add imageQueue.enqueueObj. Back in our game, we can see that it stops making new game objects after a few are created. Great, so our object pooling works. Next, we want to have the after images only appear when Santa is dashing or doing a butt slam. So let's go back to our character controller script. First, we want to make sure we have a reference to our after image script, which we'll call _after_image. We also want to be able to choose the color of the after images for dash and slam, so we will create a dash color variable. Let's set this to red. And a slam color variable. Which we will set to yellow. In our start, we want to grab the after image with getComponentAfterImage. Let's scroll down to our start dash function and add the after image there. We'll have it start just before our coroutine, and we'll simply use _afterimage.setColor dash color, and then _afterimage.startAfterImage. To stop, we'll just add it to the end of our coroutine where the dash should stop. Back in our after image script, we want to get rid of the call in our start. But since we don't actually need a start or an update, we can get rid of these completely. Back in the game, the after images no longer show up in our regular movements, but they will show up when we try to dash. The dash is a little short, so let's increase the duration. Much better. Let's go back to our character controller script and add it to the butt slam. We'll do the same thing at the end of our start slam function. Just as our dash, we'll use _afterimage.setColor slam color, and then _afterimage start after image. To stop it in our slam, we'll change it in our checkGround function. We'll add additional lines where we set is slamming to false. We want to make sure we aren't accidentally stopping the after image if we are dashing. So we'll add an if not dashing, then stop the after image. In our game, we now have a yellow after image for every time we butt stomp. If we want, we can also adjust and change the colors in our inspector.
And that's a wrap for part 4. Hopefully this effect is useful for you, not just in this project, but for other projects in the future. And as always, if you have any questions, comments, and concerns, be sure to leave it in the comments below. And if you like this video, be sure to hit the like button and the subscribe below. This is a new channel, so any support would be greatly appreciated. And with that, I will see you in the next one.